In this hour, we will talk about the concept of mode excitation. We already mentioned it informally in one of our previous lectures, but now we're ready to provide the formal definition. It goes as follows. Okay. Given some LTI circuit, okay, with no input, okay, so we're talking about the homogeneous case, x that equals ax, or you may have certain inputs, but they're all killed for the purpose of analysis. All the independent sources throughout the circuit are killed. Okay, they're turned off. And let S equals lambda. And although the general case exists, we're going to consider only the case with lambda being a real natural mode, okay, natural frequency, with lambda a real number be one of its modes. Okay, one of its natural frequencies. Now, exciting the mode at s equals s equals lambda, okay, means the following. Choose the initial conditions, okay, namely the initial capacitor voltages and initial inductor currents, inductor currents, such that any output throughout the circuit, by that we mean any branch voltage or current, in the circuit has the following form, is of the form y of t equals some constant depending on the initial conditions multiplied by e to the lambda t, lambda being the mode that we are exciting. Okay, so this is the definition of mode excitation, which will become clearer when we apply that to an example, which will come soon. Okay, so once again, let's consider this definition. Suppose that you have an LTI circuit and you have no inputs, okay, in the circuit. So we're talking about, let's say, x that equals ax, because we have no input in the circuit. And x, the state vector, consists of the capacitor voltages and inductor currents. Okay. Now, the natural frequencies of the circuit is the eigenvalues, okay, are the eigenvalues of the A matrix. And suppose that they are at S1 equals 0, S2 equals minus 2, and S3 and 4 equals minus 3 plus minus J5, let's say. Okay, so we're talking about 1, 2, 3, 4, a fourth order circuit with 4 natural frequencies. Now, since there is no input, the response will be natural response, okay? And the natural response will, in general, for an arbitrary set of initial conditions, will be composed of certain terms, and those terms are determined by the natural frequencies. For instance, S1 at 0 will produce the term e to the 0 times t, which is for all t constant. Therefore, this will produce a constant term, c. Okay, or let's call it 1 for the sake of simplicity. This will produce a constant term. This guy will produce e to the minus 2t. Okay, and this guy will produce e to the minus j minus 3 plus j5t, and e to the minus 3 minus j5t. And for they can be written as linear combinations of cosines and sines. In other words, these will yield what? E to the minus 3t cosine 5t and e to the minus 3t sine 5t. Okay? So that means for arbitrary set of initial conditions, you go and check any voltage or current in the circuit, and what you will read y of t equals a linear combination of those 4 terms. Okay? Now, what we want to do with mode excitation is we want to choose the initial conditions very cleverly, so that although in general all these 4 terms will appear in our circuit, we want, for instance, everything throughout the circuit be something times e to the minus 2t. That is, we want to suppress the terms due to these pair of modes and this mode. Okay, or we want to choose the initial conditions so that all the currents and voltages in the circuit, at the instant that we start the circuit, they're all constants. Okay, so the circuit already starts in steady state. And that's also possible because we have a natural mode at, natural frequency at s equals 0. Okay. Now, how are we going to do that? How are we going to suppress the unwanted modes? Let's say for that we will use 2 very simple facts. Okay. Some useful facts. Okay. This is one of the observations that we will use. Given a circuit with state formulation, x dot equals ax. Therefore, we're talking about a circuit without any input. If the solution is x of t equals x0 times e to the lambda t, okay, then any branch current or voltage throughout the circuit will be of the form y of t equals some constant times e to the lambda t. Lambda is the mode that's being excited. Okay. Now, why is this fact true? Okay. Or why does that fact hold? It's very simple to see. Okay, so this is the state formulation. So our circuit have no inputs. Okay. And suppose that this is the solution of the state equation, x of t equals x of 0 times e to the lambda t. Okay. Now, since the state x is our capacitor voltages and inductor currents, that is the variables related to our dynamic components. So that means all the capacitor voltages and all the inductor currents will be of this form, something times e to the lambda t. Okay, because x is our capacitor voltages and inductor currents. And then what we can do is we can just apply substitution theorem and replace all the capacitors with independent voltage sources that provide voltages of this form, and replace all the inductor currents with independent current sources who provide currents of this form, okay? And then once all the dynamic components are replaced by independent sources, the circuit clearly becomes LTI resistive with all the inputs in the circuit of this form. And then by linearity, clearly all the outputs in the circuit will inherit the form of the input, which is something times e to the lambda t. The other fact that will be useful for mode excitation is the following. Given x that equals ax, let lambda be a real eigenvalue of A matrix with the corresponding eigenvector denoted by V. Okay, so let's remember the eigenvalue-eigenvector equation. That is AV equals lambda V. Okay, or we can write lambda I minus A times V equals 0. That is, V, eigenvector, belongs to the null space of this matrix, lambda I minus V. Then we say V, if non-zero, because by definition an eigenvector must be non-zero, V lies in the, if V, a non-zero vector, lies in the null space of this matrix, then we say this is an eigenvector corresponding to the eigenvalue at lambda. Okay, now for such state equation, suppose that this is representing some LTI circuit. And now, if we choose the initial condition of the state x0 equals V, that eigenvector, okay, the solution corresponding to that is x of t equals e to the lambda t. Okay. Now, in general, we know that the solution to homogeneous state equation is e to the at times x0. Okay. For any initial condition. Now, e to the at is the matrix exponential. It has many terms, and in general, therefore, and all those terms will be related to all the natural frequencies. Therefore, in general, this x of t will be quite complicated in form. It will contain all the natural frequencies. Okay, like here, a constant term, e to the minus 2t term, and those oscillatory terms. Okay, but if you start with the initial condition, a very special initial condition. It's special in the sense that it's eigenvector of one of the natural frequencies or one of the eigenvalues of A, then the solution, which in general would be a little bit complicated, has this very simple form. Okay, the initial vector times that scalar e to the lambda t. Okay, now combining these two facts, we can now apply this definition to a simple numerical example. And through it, hopefully, we will understand mode excitation better. Now here is our example, a circuit of order 3. Consider the below circuit with 3 dynamic components, 1 inductor and 2 capacitors, and for the inductor somehow we're given the initial condition, but the initial conditions of the capacitors are not given. With initial inductor current equal to minus 3 amps. Okay, this is the circuit. Okay, 1 farad, 1 farad, 1/2 Henry, and 1/3 ohms. The directions are given as follows. This is IL. This is the first capacitor voltage, VC1. This is the second capacitor voltage, VC2. And this dependent source depends on the second capacitor voltage, and it produces the current 2 VC2. Okay, and the initial condition for the inductor current is given to be minus 3 amps. Now for this circuit, first obtain the state equation, which clearly will be in this form. Okay, it will be a homogeneous equation because we have no inputs in the circuit, we have no independent sources. Once we obtain the state equation, then we're asked to find the initial capacitor voltages okay, VC1 0 and VC2 0, such that the response, which clearly is a natural response because we have no input in the circuit, the response does not display any oscillations. Okay, so what we're asked in B is not that crystal clear now, but it will become more meaningful once we figure out the natural frequencies of the circuit. But for that, we first need to figure out the state equation, okay? In other words, the A matrix. Okay, now let's allow me to skip details, okay, for the part A, and let me directly put on board the equation x equals ax. It's not really that difficult to obtain the state equation. For the state choice, VC1, VC2, and IL, namely, our state contains all the capacitor voltages and inductor current. One obtains the following state equation: x dot equals Ax, where A equals this matrix 0, minus 2, minus 1, 0, minus 3, minus 1, and 2, 2, 0. Okay, so that would be a nice exercise to derive this equation for the given state choice. Okay, now once we have the state equation, in other words, once we have the A matrix, it's really straightforward to obtain the natural frequencies because we know that natural frequencies of the circuit are the eigenvalues of the A matrix. Okay. So what are the natural frequencies? We know that they are the eigenvalues of the A matrix. More formally speaking, they are the roots of the characteristic polynomial of this state equation, or this A, or this matrix, which is d of s equals determinant of Si minus A. Okay, so A is a 3×3 matrix. Therefore, characteristic polynomial will be a polynomial of degree 3. And then we will have 3 natural frequencies, okay? Which is what we expect because the circuit is of order 3. Okay. Now, let's quickly compute that characteristic polynomial from which we can extract the natural frequency information. And then, once we have that natural frequency information, what we're asked in part B, that is, choose the initial condition so that the response does not display any oscillations, will become more meaningful. Okay, characteristic polynomial E is the determinant of Si, which is this diagonal matrix with S's in the diagonal minus the A matrix. 0, minus 2, minus 1, 0, minus 3, 2, 2, 0. Okay, and this is the following determinant: S2, 1, 0, S plus 3, 1, minus 2, S. Okay, so d of s equals these entries multiplied plus these 3 entries multiplied plus these 3 entries multiplied minus, then you do the opposite thing in the reverse direction. So what we have is therefore s squared, s plus 3 minus 4 plus 2 s plus 3, okay, and finally plus 2s, okay, and that equals s cubed plus 3s squared plus 4s plus 2. Now, this is our characteristic polynomial, namely determinant of that matrix, Si minus A. Now, this is a third order polynomial. It's not easy unless you have a root at the origin. It's not easy to see the roots directly. So, suppose that by some chance or by using MATLAB or something else, we figured out the following factorization: s squared plus 2s plus 2. Okay, so our characteristic polynomial can be written in this form. Okay, then we see that we have an eigenvalue at -1, and then this second order polynomial will produce a complex conjugate pair of natural frequencies, eigenvalues. So let's rewrite the s as s plus 1 plus j and s plus 1 minus j. Okay, so that means we have one eigenvalue or one natural frequency at -1, and then the other two are a complex conjugate pair at -1 plus minus j. Okay, so let's write them down. The natural frequencies, or the modes of our circuit, are S1 equals -1, and S2 and 3 are at -1 plus j and -1 minus j. Okay. Okay, so let's put this in a box. Note that since we're dealing with real valued A matrices, which will always be the case because we're dealing with a real circuit. Whenever we have a complex root, its conjugate must also be one of our natural frequencies because the coefficients of the characteristic polynomial will always be real. Okay, now having obtained the eigenvalues of the A matrix, we can make some conclusions. Okay, we can reach some conclusions regarding the general form of the natural response. Okay. So, form of any output of the circuit, any branch voltage or current throughout the circuit. Okay, it has to be of this form: y of t equals. Now, in general, we mean we choose the initial conditions arbitrarily. Because of that arbitrariness, we expect all the natural frequencies, okay, to appear in our arbitrary solution. Therefore, a general solution will have something times e to the minus t, which is due to the eigenvalue or the natural frequency at -1. And then we have cosines and sines with frequency 1 radians per second, but they are not pure sines and cosines, they are decaying sinusoidal signals, and they're decaying with the term e to the minus t. So this pair will produce something, some constant times e to the minus t times cosine t, and some other constant times e to the minus t times sine t. Okay, but those two sinusoidal functions, cosine and sine, can be combined because they are oscillating at the same frequency, and we can write that two pieces as a single sinusoidal function with phase. Okay, in other words, we will have e to the k2 e to the minus t cosine t plus some phase. Okay, so note that we have three unknowns, k1, or three constants, k1, k2, and phi 2. Okay, and remember also that we have three initial conditions: inductor current and two capacitor voltages, because the degree of the circuit is 3. And those three initial conditions, okay, will determine these three constants, k1, k2, and phi 2 for the general case. Now, let's also try to visualize these terms. This is, we can call, a non-oscillatory term. Okay? Because it's monotonous, okay? It's a monotone function. Okay. For instance, it will be decaying like that. If k1 is negative, and if k1 is positive, it will start from the upper half and then decay to 0. This is t and 0. Okay. Whereas the other term, although it too decays to 0 because exponential decrease will dominate those oscillations, but it goes to 0 in a different way, not in a monotone way like that. It will oscillate. Okay. So here we're expecting something like this. Okay. The oscillations will decay to 0, but nevertheless there are oscillations due to this sinusoidal term. Okay, T0. And this is the oscillatory term. And now, once we put those waveforms on the board, it's clear what we're asked to perform in part B of the question. Part B of the question was that choose the initial conditions so that the response, okay, all the branch voltages and currents throughout the circuit do not display any oscillations. Okay, so what we want to do is we want to pick the initial conditions so that the terms are suppressed. They disappear from the stage. So that means, okay, mathematically speaking, that means we have to excite the mode that corresponds to the natural frequency, okay, at -1. Okay, so all we have to do therefore is, since we have the A matrix, we're going to figure out the eigenvector corresponding to the eigenvalue at -1, and then we're going to pick the initial conditions so that they make the x0, the initial state vector, becomes that eigenvector corresponding to the eigenvalue at -1. Okay, so therefore let's begin our part B. To avoid oscillations, excite the non-oscillatory mode. Okay, that is the real eigenvalue at -1. For that, we have to figure out the eigenvector for that eigenvalue, and let V1 denote that eigenvector. Be the eigenvector for that eigenvalue, S1 equals -1. So, that means, okay, then we have Si minus A evaluated at S equals S1 times V1 equals 0. Okay, so to figure out that eigenvector, what we do is we use the eigenvector eigenvalue equation. In other words, construct the matrix Si minus A, plug in S equals the eigenvalue for which you want to find the eigenvector, okay, and construct this matrix, okay, S1 times identity minus A. And then by definition, the eigenvector corresponding to the eigenvalue must belong, okay, to the null space of this matrix, okay, and then once you have this matrix, it's easy to figure out its null space, and then from that null space information, we will have the eigenvector that we are looking for. So, minus I minus A times V1 equals, now plug in S1 equals, S equals -1, so what we have it here is minus I minus A, I being the identity matrix, and that equals, since we have the A matrix already, that equals this matrix times, okay, minus I minus A times V1, our vector in R3, equals 0. Okay. Now, this matrix is -1, 2, 1, 0, 2, 1, and -2, -2, -1. And V1 is our unknown, at this point, eigenvector. So let's label its individual entries by A, B, C. Okay. And now we're going to figure out A, B, C by looking at this equation. So let's write this single matrix equation as 3 individual scalar equations. For the first row, we have minus A plus 2B plus C equals 0. The second row gives us 2B plus C equals 0. And the third row gives us minus 2A minus 2B minus 2C equals 0. Excuse me, this is minus C. Okay, now 2B plus C equals 0, minus A plus 2B plus C equals 0, so it means that A must be 0. And then we don't even need the third equation. okay? Because necessarily these three rows are linearly dependent. Why? Because this is a singular matrix. Therefore, we can look at this equation once again, and we should have what? C equals minus 2b. So what we have is A is 0, B is, let it stay B, and C is minus 2b, okay? And then for any b, any non-zero b, that would make an eigenvector for the eigenvalue at minus 1, okay? So we have therefore 2b plus c equals 0. Hence, hence V1 equals A equals 0, B, okay, let B stay as it is, and minus 2B is the eigenvector for S1 equals minus 1, okay, for any non-zero b, because if b is 0, then v1 is 0, but by definition an eigenvector must be a non-zero vector. Okay, now we have figured out the form of the eigenvector, or the one-dimensional subspace of R3 where our eigenvector must belong to, okay, and finally we can apply the necessary constraint on our initial conditions so that only this mode is excited. Now, what we want is, we want x0 equals v1, because if you let the initial condition to equal, or the initial state to equal the eigenvector, then the solution, state solution, will simply be that eigenvector times e to the s1t, in this case e to the minus t, because then x of t equals v1 e to the s1t, which is v1 e to the minus t, okay? And if x of t is v1 times e to the minus t, that means all the capacitor voltages and the inductor currents will be of this form, something times e to the minus t, and then consequently all the other branch currents and voltages will be of that form. In other words, there will be no oscillations. Okay. Now, so the answer is, well, the rough answer is that, or the raw answer is that if you choose any B, okay, and you start your circuit from this initial conditions, the first capacitor voltage 0, the second capacitor voltage is something 6, and the inductor current minus 12, then your circuit displays no oscillations. Or pick another B and set the initial conditions to that, and then your circuit displays no oscillations. Okay, so there are infinitely many ways to start your circuit, but since the initial inductor current is given, we cannot pick B arbitrarily. Okay, so that initial inductor current will set the B, and we will have the unique answer for our question, okay, in part B. So now we want that. So let's apply therefore the initial condition, constraint 0b minus 2b, okay? This is the eigenvector, and we want this to be our initial condition. That is, we want this to equal Vc1 0, Vc2 0, and IL 0. Okay? And we're already given the initial inductor current, so this is minus 3, Vc2 0, Vc1 0. Okay? And so this equals that, will immediately and uniquely determine B and then eventually VC20 and VC10. So minus 2B must be minus 3, therefore B is 3 over 2. Hence VC20 must be 3 over 2 volts and VC10 must be 0 volt. Okay, therefore B equals 3 over 2. And then VC10 equals 0 and VC20 equals 3 over 2 volts. Okay. To summarize, if the initial inductor current is given as minus 3 amps and if you don't want any oscillations to appear in your response, then that's possible only by choosing the initial capacitor voltages as 0 volt and 3 over 2 volts.